Welcome to part 4 of neural networks in Cuda from scratch. Last time we implemented the feedforward method for multiple layers. However, one limiting factor is that right now we are only using a single input vector. A modern GPU can run thousands of threads at once, so we should make use of that opportunity and code our kernel so it passes multiple inputs through the neural network at once. Until now, we just had a list of threads. In this list of threads, each thread corresponded to a specific neuron in the current layer of our neural network. Now that we want to take care of multiple inputs, we are going to change that. In our new threading strategy, we will have one thread per neuron for every input. So we are going to use a thread block. Going from left to right, we have our usual list of threads, where each thread takes care of one neuron. Going from the top to the bottom, we now have rows of threads for every input. We can access the neuron index via the thread idx.x variable. We can access the input index via the thread idx.y variable. In this example image, we have 3 inputs and 6 hidden neurons, therefore resulting in 18 CUDA threads. Alright, let's have a closer look at what each individual thread will do. We're going to use the following example to visualize everything. We use a simple neural network with 4 input neurons and 3 output neurons. The input matrix will consist of 3 inputs. Therefore, we will need 9 threads. 3 threads in the y dimensions, 1 for every input, and 3 threads in the x dimensions, 1 for every output neuron. Now let's have a look at what every single thread does. Alright, so thread 0 with the x coordinate 0 and the y coordinate 0 will take the first input and compute the activations for the first output neuron. Thread 1 will also take the first input, but will take care of the next output neuron. And thread 2 takes care of the final output neuron. Next, we move on to thread 3 up to thread 5. These 3 threads will take care of the second input. The coordinates for thread 3 are x equals 0 and y equals 1. So it takes care of the second input and the first output neuron. Thread 4 takes care of the second output neuron, but also uses the second input. The thread coordinates here are x equals 1 and y equals 1. I'm sure you can guess what the other threads do now. So let's move on to the next topic, the data structures. Now that we want to handle multiple inputs, we need to change our memory structure. The structure of the weights and biases stays the same. But we need to change the activations array and the set value array to accommodate multiple inputs. This is the current structure we have now. Let's change this structure so we can have multiple activation vectors and set value vectors. Take a look at the new memory structure. The order of the layers in the memory stays the same, but each layer section now holds multiple inputs, instead of just a single one. There are 2 changes we need to do to the code in the main function. We need to change how we call the kernel, and we need to change the data structures for activations and set values to be compatible with multiple inputs. So now we need to call the kernel a little bit differently. The main thing which changes is that now we need more threads. We need 1 thread per input and neuron. So if we have 3 inputs and 6 neurons, we need 18 threads. We can specify this via a 2-dimensional tuple, which specifies the dimensions of the thread block we are going to use. The number of threads in the x dimension is going to be equal to the number of neurons the largest layer has. and the number of threads in the y dimension is going to be the number of inputs. That's it for the kernel call. Now we move on to our data structures. Now let's have a look at a side-by-side comparison of the code from the previous video to our current code. First, we introduce a variable which defines the number of inputs. Next, we need to change the size of the activations array. Previously, the number of activations was the same as the number of neurons. But now we need one set of activations for every input. So we need to multiply the number of neurons with the number of inputs. Another thing we do for the activations array is to initialize it with enough values for 3 inputs. So that's why the list is longer than in the previous code. Let's move on to the set values array. Here we encounter a similar situation. Previously, the number of set values was equivalent to the number of biases, but now we compute a bunch of set values for every input. So we need to also multiply with the number of inputs here. So in this line, we just change the code, so we use the previously computed variables. The final thing left to do is to adapt the printing of the activation and set values to the new data structure, so we can verify and compare them. I'm going to skip over these changes as they are not interesting. Alright, so next let's change our kernel code so it can handle multiple inputs. On the left you can see the old code, and on the right you can see the new code. The new code can handle multiple inputs. The first change we're going to make is to have separate offsets for the set values array and the bias array, since the set values depend on the input number while the biases don't. Previously we could use the same offset for both arrays, but now they are different. Also, for convenience, we will add a offset for the activations which will be fed into the current layer, and another offset for the activations the current layer will produce. The variables only take care of indexing into the correct layer, but they don't take care of individual inputs or neurons. One detail about layer offset activations current layer, we initialize it to shape 0 times block dim.y. Shape 0 is the number of input neurons, and block dimensions.y refers to the number of threads in the y-axis, which in turn refers to the number of inputs. The next change is we save the layer size of the current layer in a variable so we can reuse it in the next few lines. So for the computation of the weighted sum, weights times activations, we must change the indexing for the set values and activations. The indices for the weights stay the same, since they are input independent. For the set values, we add thread idx.y times layer size, where thread idx.y refers to the input the current thread has to take care of, and we multiply it with the layer size. Here is a small animation which explains the indexing. All the threads with thread idx.y equals 0 will take care of the first input, because 0 times 6 equals 0, which is the beginning of the array. The threads where the thread idx.y variable equals 1 will take care of the second input. Now, when we move on to the next layer in the neural network, we will have layer offset set being so that the pointer points to the set values of the next layer. Apart from the offset moving us into the correct layer, the indexing logic stays the same. The thread idx.y variable will help to point us towards the correct input, with the same formula thread idx.y times layer size. Obviously, the layer size is now different since we have 4 neurons instead of 6, like in the first layer. For the activation values, which represent the inputs to the current layer, we add thread idx.y times number inputs to this layer to the index. Just as an example visualization, let's consider the threads where thread idx.y equals 1. These threads will compute the weighted sums and activations for input number 2. To compute the weighted sum, these threads have to index into input number 2 of the input layer. For the first iteration, the layer offset will be 0. The product of thread idx.y times number input to this layer helps us to point into the correct input inside the layer. The inner for loop iterates over all the values of the input vector, so it gives us all values from 0 to 8 for the neuron number. This indexing scheme therefore allows us to get the correct inputs for each output. To finish the set value computation, we also need to add the bias. The indexing for the set value follows the same logic as in the line above. The indexing into the bias array is the same as from the previous video. Alright, so the last step is to compute the sigmoid function. So the indexing logic for the set values will be the same as in the lines above. And for the activations, it will be very similar too. The difference is that we use the activation's current layer offset variable instead of the layer offset set variable. That's it for the computation. At the end, we update all our layer offset variables. Basically, we just change all the layer offsets so they point one layer further. We do this for weights, biases, set values, and activation offsets. You can see this illustrated in this image. Now let's run and test our code. Alright, now on the left here we have the Cuda code. And on the right we have the Python code for verification, which does the neural network forward pass with NumPy. We use the exact same weights and biases as in the Cuda code. And also we use the same inputs. If the Cuda code produces the same results as our Python verification program, we can be sure that our Cuda code is correct. Let's run the Cuda code first. Alright, so these are the results we get. Now let's run the Python code. Alright, so now let's compare and see if they are the same. Yes, the values are the same, so this means our Cuda implementation is correct. Alright, that's it from this video. As usual, all the code can be found on GitHub. In the next video, we will implement the backpropagation algorithm. Thanks for watching.